Okay. So, last time we were talking about R1 and R2, and we still have a lot of stuff to say about them. Let's see. We'll say we'll do this in two columns, a left column and a right column, and that's going to be. Well, let's think about this. What's the easiest way to say this? No, maybe I'll do it with a R1 column and an R2 column. So R1 on that side, R2 on this side. So we talked about comparing these two. We talked about handedness. Concerning these, there's going to be two kinds. So left-handed and right-handed. So left-handed R1 looks like this. So it's left-handed, because it's pointing to the left. What that means is that for this R1, as you move to the left, the numbers get bigger. So it would, be like, 3, 4, 5, 6, etc. And the reason for the barbs looking the way they do, before we got into this point of view, we'd usually draw R1 as a horizontal line, but write the barbs going like this. And that would mean that it's going all the way to the left and also all the way to the right. But now this means we're going all the way to the left, and that one means we're going all the way to the right. And the reason why they're both pointing that way is because we want it to be clear that the world is going that way. So that's the direction of the world. Sort of like, you might think of it like a river. It goes that way. It doesn't flow both ways. Okay, so that's left-handed, and then this right-handed. So left and right. Okay, and it's as simple as that. When you're looking at this, looking at the page from the standard point of view, that one is pointing to the left, that one is pointing to the right. Now R2 is you take two copies of R1, so one copy and another copy, and you make them be at right angles. So one copy and another copy, and one copy and another copy. So besides the handedness convention saying that this one is left and this one is right, we also have another convention which says that unless we've got a good reason to deviate, we're always going to make stuff right-handed. Okay, so that means that for both of these, I'll make the horizontal axis going to the right. But nevertheless, I want this to be the left-handed plane, and I want this one to be the right-handed plane. And the way that we're going to do that is that notice in both cases we haven't yet illustrated which direction the vertical axis is going, right? For this one we haven't said up or down, and for this one we haven't said up or down. So one of them needs to be down and the other one needs to be up. And we want to make it to where one of them is going to be left-handed and the other one's going to be right-handed. So here's the idea. So if you stir a cup of coffee, or a pot, or whatever you like, then the stirring is going to happen like this. Is that R2 is two copies of R1. We'll refer to the horizontal axis as the first axis. So that's the first axis, and the vertical copy as the second axis. And the way we're going to stir is that we're going to use these instructions. So we're going to follow the first axis a little. Then we're going to follow the second axis a little. And then we're going to loop back. You know, because we're stirring a pot, not an ocean, right? Okay. So if you take your left and right hands, if you take, for example, your left hand and hold your left thumb up and put your hand on the page, like that, then your fingers curl towards your palm, like this. So from your thumb, your fingers go like that. And that's the direction of the clock. It's clockwise. So left-handed stir looks like this. So it goes with the clock. Right-handed so now, again, take your hand, but now your right hand, hold your thumb out and put it on the page. Your fingers curl towards your palm, and that is counterclockwise. So, you know, like this. Okay. So now we want this to be right-handed. And if the stirring rule is that you follow the first axis a little and then the second axis a little, that means that because, you know, we choose any point, so say I'm gonna stir from that point, we're going to go to the right in both cases because it says follow the first axis a little. So from this one we're going to go right, and from this one we're going to go right. But if we want to end up going counterclockwise for this one, after we go right a little bit, how do we have to go? We've got to go up to go counterclockwise. So we have to go right and up, which means that this has to be pointing up. And then the opposite on the other side. So we're going to go right a little bit, and then to have, you know, from here, you know, we have to go either down or up after we go right a little, and we need to go down because we want to go with the clock. Okay, so that means like this. Okay, interesting. Fine. So that's the handedness convention. So also notice that there's a mirror symmetry. Symmetry. And that is that if we have a mirror, so now imagine that you're looking at maybe you're getting ready in the morning or something, and you're looking at yourself in a mirror. And now imagine holding your right hand up, and you're looking at yourself in the mirror. Then what hand is the person in the mirror holding up? Yeah, they'll be holding up their left hand. So if you're looking at a full-length mirror, holding up your right hand, and if you were to go up and give yourself a high five, right, just blah, then what hand would that person in the mirror be holding up? Their left hand. Okay, so the way that what that has to do with this situation is that in R1, the left-handed R1 looks like this. That's left-handed R1. And then if you were to take this and reflect it across the mirror like this, so sort of pick it up and whoop, so that kind of thing, then notice that that barb is going to be far away from the mirror. So when you reflect this one across the mirror, you get left to right, right to left. just like your hand when you're looking in the mirror. In the case of R2, left-handed swirl looks like this. So left-handed swirl would be like this. So we start there, and then come back and follow the clock. And then if we were to reflect this to the other side, so not just pick it up and move it over there, but reflecting it, then notice that here's the mirror and here's the swirl. This is like the near side of the swirl, and that's the far side. Notice that the far side is where the barb is. So that means that this would reflect like so, to counterclockwise. So can you see it? And then this is not really part of our class, but it may help you to understand that this pattern continues. So just like this is the one-dimensional symbol for left and the one-dimensional symbol for right, the two-dimensional symbol for left, the two-dimensional symbol for right, there's a three-dimensional symbol for left. The three-dimensional symbol for left is this. The reason why is that if you can imagine that that's like a loop and there's an arrow going through it, notice that if I make my thumb parallel, my left thumb parallel to that arrow going up, then my fingers are curling in the same direction as that circle. So that's the three-dimensional symbol for left-handed. And then if you reflect that to the other side, then that arrow is still pointing up. But now, like this. So now I hold up my right hand and my fingers are in agreement. Okay, interesting. So, this is more than just like a mathematical fancy because of an example like the following. So there's a disease, a very terrible disease called Creutzfeldt-Jakob Disease. So that's the name of the people who found it. But it has a much more common name. Does anyone know the common name of Creutzfeldt-Jakob disease? It's also called Creutzfeldt-Jakob disease. It's called mad cow. It's a mad cow disease. So, we're just made of like atoms in the end. If we had really good vision, and you could look real close at your hand and like see the atoms. But of course we can't do that. The atoms are arranged in molecules, which is just the atoms are all bound to each other. Which means that, this could be one atom, and then if it looked itself in the mirror, it could see its reflection, back and forth. Right? So, Creutzfeldt-Jakob disease is actually something that looks like this, is that there's a carbon and a carbon right in the middle. And then if you come out of the page a little bit, or no, this out of the page looks like this. If you come out of the page a little bit, there's another atom that's right here, like this. So I'll just call this A1 for atom. And then you come out of the page, there's another atom right here, A2. And then into the page, going that way, there's an atom right there, A3, and then coming up like this, there's an atom right there, A4. So that just means that these two are sort of coming out of the page, and that one's going into the page, and that one is parallel to the page. And then if you reflect this, then this looks like this. So this is still A4. These are still coming out of the page. But notice that A2 is closer to the mirror. So which one of these is going to be A2? That one is, right there. So A2. And then this will be A1. And this will be A3. And now the reason why this is significant is that all that Creutzfeldt-Jakob disease is, all that mad cow is that there's a protein that has a particular carbon, and I don't remember which one is the good one and which one's the bad one. So I'll just say that left one is the good one. So there's a particular carbon, and it's shaped like that, and that protein does something useful in your body. I have no idea what. So it's used in your body. And then if ever, by a freak accident, your body accidentally makes that one, or if you eat meat that's been tainted with it, then you could get this right-handed version. Now that happens all the time in your body. That on accident, a left-handed protein turns into a right-handed protein. But mainly, your body just either looks at that and automatically corrects it, or it just takes that protein and just breaks it down into its parts and makes a new protein with it. So it happens all the time. But in the case of Creutzfeldt-Jakob disease, what happens is that this one is good, and its reflection is not useful, but the reflected molecule has the very sad property that if it ever hits the left-handed one, if it ever comes in contact to a left-handed one, it turns it into another right-handed one immediately. So it's a catalyzed reaction. So if the left one is the good one, if there's even one right-handed version of it, it very quickly will turn all of the left-handed ones into right-handed ones. And that means that protein, the one that you actually need, you can't have, because every time your body makes one, it's immediately turned into the other kind. And that's what Creutzfeldt-Jakob disease is, and that's why there's no cure. It's a really sad deal. Okay. So besides the sadness, any question about the symmetry issue? Okay. So now, concerning that, we have distance. So in R1, we have two varieties of distance. We have signed distance. So the signed distance from A to B is, so this is frequently referred to as the initial point, and this one the final point. So initial and final. So the formula is that the distance is, so this is a extremely common phrase in physics. It's always final minus initial. So it'll be B minus A. B minus A. And then the sketch of it, the way it looks, is like this. So we could have, for example, a right-handed world, and we have 2 points, say, and maybe we have another right-handed world with 2 points. So if this is A and this is B, then if we want to go from A to B, so initially at A, traveling toward B, so that would mean that we draw, starting here at A and then travel toward B. Now, to indicate the direction we were traveling, I'll make a barb, because we were going A to B. So do you notice that the direction of travel is the same as the world in this case? You could think like if maybe the world is like a river and you're going with it. Same direction. So in this case, d is positive. Okay, but if it looks like this, so again, the initial point is A and the final point is B. That means that we're going to start here at A, so that's where we start, and then we're going to travel to B. And then, you know, to record the direction that we traveled, I'll make a little barb. And do you observe that we went against the world? We went in the opposite way of the world. All right. So that means that in this case, d is negative. All right. So, you know, just as a note, interpreting what this means, is that if we draw a right-handed world, or a left-handed world, it doesn't matter, and then suppose I indicate the value, the location of 0. So there's 0. And then suppose that we have a ruler that we've agreed on. You know, I don't mean an autocrat. I mean a linear measuring device. Then I could say, well, how many points, according to the ruler, have distance 3 from 0? How many of them? Well, it'll be 2, right? The ways we can arrange the ruler. So there'd be this one here, and this one here. So they both have distance 3. So but and that means that for both of those points, 3 is going to be part of their name, but they can't both be called 3 because they're not the same point. So they can't have the same name, have to have a unique name for every point. So one of them is going to be negative 3, and the other one's going to be positive 3. Now, which one is going to be negative 3 and which one's going to be positive 3, and why?
The one on the left is negative 3 because the world is going right.
Okay, good. So this is going to be negative 3. So that's going to be negative 3 because the name for a point, what it is that you start at the origin. So origin means where you start. You start at the origin and then go to that point. So if we start at the origin and go to this point and record the direction we were traveling, then do you observe that from the origin to that point, we were going against the world? So that's negative 3. And similarly, this one is positive 3. And then under normal circumstances, you would not write the plus sign. You just write 3. Fine. Then besides signed distance, there's something called unsigned distance. So, well, let's have an example before we do the next thing. So, example. So the signed distance from 2 to 10. So from 2 to 10. So then the formula is saying what? So formula would be d equal to, and then what do I have to write? Sorry? Right. So final minus initial. So that would be, in terms of these numbers, that'd be 10 minus 2. So that would be that'd be 8. That's what the formula is saying. And then giving a sketch of it, if we draw a world, then we'd want to plot both of those points. Now, because I drew a right-handed world, that means that the numbers get bigger to the right. So I'll draw 2 points, so 1 and then another. And we need to plot 2 and 10. Which one of them needs to be 2? That one, because it's the smaller one. And then like this. So, if we travel from 2 to 8, starting at 2, going to 8. Not 8. What am I saying? It should be 10. If we start at 2 and go to 10, then if we got out the ruler and measured that length, it would have length 8. And moreover, because we're going with the world, we would say that that's positive 8. So it's 8 and with the world. So that has length positive 8. Okay, whereas the signed distance from, say, 7 to, what do I want to do? So 7 to 2. So the formula is D is going to be what? In terms of just the numbers. So this one was 10 minus 2. What's this one? 2 minus 7, because it's always final minus initial. So it's always final minus initial. So then 2 minus negative 7, that'd be negative 5. So, interpreting that, what that means is that when you travel from 7 to 2, the length that you travel is 5. That's how far you go. And moreover, you are going against the world. You were going upstream. So it would look like this. So from 7 to 2. So we start at 7. And then we travel to 2. And the direction of travel was like this. So the length of that thing that I just drew, that has length 5. And because it's going against the world, we're calling that negative 5. Any question about it? So now, very often in the real world, we're not actually interested in sign, as in negative and positive. All that we're interested in is just the length. So an example would be something like, suppose that you're going to travel from the Dallas area to the Houston area, and suppose that it's exactly 200 miles. So maybe you're going to do that this weekend, maybe, I don't know. And it's 200 miles, Dallas to Houston. So what about then Houston to Dallas? Also 200 miles, right? It's not negative 200 miles. That'd be great if it was, wouldn't it? Because that would mean on your way back your gas tank would fill up. But okay, it doesn't happen that way. So the unsigned distance from A to B is, so the formula is just going to be So what we want is we want a formula that basically says, well, it's the signed distance, but we want to sort of just ignore the sign. So, you know, if Dallas to Houston is 200, the signed distance, then Houston to Dallas would be negative 200. But suppose we want to get 200 in both cases. So then what formula can we use? Absolute value. So we can say absolute value of b minus a. So that'll get it for us. So that's saying that the unsigned distance is the absolute value of the signed distance. Okay, fine. All right. Any question about it? Okay. So now what we want is, so this is a continuation of that page. So for two, we want a R2 distance. Now here's the first interesting thing. So in R1 we have signed distance. We can say, is it going to be 5 or is it going to be negative 5? But for R2, R2 only has unsigned distance. So now here's the reason. So if I make a little R2 world for us, and then I could say, well, suppose that we want to travel from here, from this point to this point. So we want to travel from that point to that point. Then, you know, I can draw the little interval that goes like that. So I drew the interval. And moreover, because that's the initial point and that's the final point, I can even draw a little barb for myself. Now here's the thing, is that it's not possible to interpret that as being to the left or to the right. The reason is because, what if you were looking at it like this? What if you were standing right here? This is an eyeball. So you're like standing there and you're looking at it. So from that point of view, it looks like it's going to the right. Okay, so that looks like it's going to the right. But if you walk around to the other side and look at it like this, then what does it look like now? Looks like it's going to the left. So from this point of view, it looks like it's going to the right. And from this point of view, it looks like it's going to the left. And, you know, that's just a matter of walking to the other side. Now, in R1, you know, the way it works is that R1, the world is one-dimensional. So, like, you can't look at it from above. Okay, you have to stay in the world. So you can't, like, look at it from above and below. Whereas this, you can look at it from that side and that side. Okay, so that means that there's no sign. All right, so let's find the distance. So the unsigned distance. All right, so here's how we're going to do it. Make myself a little little R2 world. Okay, and remember that the convention is that an R2 is 2 copies of R1, so first copy, second copy, and they're at right angles to each other, so right angles. And suppose that this is the initial point, and this is the final point. And I won't bother drawing the barb, I guess. So init. Final. I guess I'll draw the barb. And what we want to know is what is this distance, and I'll call this I'll call it d. So we want to find d. And here's the tools that we have. Is that we have 2 copies of R1. Now on each one of the copies of R1, we have signed distance and distance. We have them both. So that means in some sense that if we had points on this axis, we could start measuring stuff. And if we had points on this axis, we could start measuring stuff. You can kind of think of it like we have a ruler that's allowed to be held horizontally, and we have a ruler that's allowed to be held vertically, but it is absolutely forbidden for some reason to hold the ruler at an angle. So you can't do that. That would be against the rules. Okay. So what we need to do is we need to turn our horizontal and vertical information into information that can be slanted. All right. So here's how we'll do it. Is that imagine that I've got a bright flashlight up here and it's shining very, very bright, and then this line segment is casting a shadow on the horizontal axis. So it's very, very far away. This light source, very, very bright, is casting a shadow. So can you see the shadow it would cast? It would cast that shadow right there. Well, that gives us 2 points on the horizontal axis. Okay, so I'll call this one x1 and this one x2. And now I'll do a similar trick. I'll say, okay, so now the flashlight is shining that way, very, very bright, and this is casting a shadow, but it's casting its shadow on the vertical axis. It's casting its shadow on the vertical axis. So the casted shadow would look like this. So now that gives us 2 points on the vertical axis. So now I'm going to want the coordinates of this point. I'm going to call it x1, y1, and I'm going to call the coordinates of this point here x2, y2. So I just wanted these both to be 1, so x1 and y1, and I wanted these both to be 2, x2 and y2. So that means that what's the name of this point? What's its value? Yeah, so this is a you could call it a y value. So in the end, what I'm asking is that right here, am I going to write y1 or y2? Y2. Y2 because that the height is coming from this one, so it's y2. And what you know is obvious now, but what am I going to write right there? Y1, because that's how high this is. So y1. Okay, so now you know we found some places we can measure on these axes, and now because these axes are at right angles to each other, that means that this also is a right angle. That's a right angle, and therefore this is a right triangle. This is a right triangle, and you know, we've arranged matters so that the distance that we want is actually the hypotenuse of a right triangle. So you know, remembering that stuff from grade school. is that a right triangle is a triangle where one of the angles is a right angle. The side opposite of the right angle is called the hypotenuse. Okay, and then typically in grade school, you'll write that that's C, and then the name for the two other sides that aren't the hypotenuse, these are called legs. So this is called a leg, and this is called a leg. And you know, typically this might be named like A and this B, like that. And then the Pythagorean theorem says what in terms of A, B, and C? Very good. A squared plus B squared is C squared. Well, okay, we need to just play exactly that game, but with this diagram now. So the hypotenuse is what we're looking for. So that's what we want in the end. So what we need to find right now is the length of the legs. So what's the length of this leg? Okay, so that would be x2 minus x1. All right, and what's the length of this leg? y1 minus y2? But wait a second, I thought we were doing 2's and 1's, like x2 minus x1. Why not y2 minus y1? Okay, because y1 is the bigger one, right? So I'm going to write, just to make sure, just so that this is 2 minus 1, like that, I'm going to make this one the same way. But y'all have rightly observed that that couldn't be correct. Whoops. That couldn't be correct because the way that I wrote that, y2 minus y1, that means that we'd be traveling from this point to that point. But that's going against the axis, so that'd be negative. So to get the positive version, we'd want that. But if you would have said, even though y'all rightly said y1 minus y2, I can make a different drawing where it needs to be y2 minus y1. So how do we make sure that we're always getting the right thing? Well, what we have to do is that this right here is a signed distance. But what we really want is unsigned distance. So how do I make this unsigned? From the previous page. Absolute value. So absolute value, absolute value. So can you see it? All right. So the Pythagorean theorem is therefore telling us the following. That the hypotenuse squared is, we'll take the horizontal leg length and square it, and we'll take the vertical leg length and square it, and then we'll add those together. So that's the Pythagorean theorem. And then we want to have a nice formula for this. So I'm going to make an observation. So I'm going to write something, and then y'all tell me what it is that I did and whether or not it's legal. So in the first place, what did I do? Yeah, I removed the absolute value, which seems questionable because didn't I just make a big point about saying, oh, we have to have the absolute value? And then now I'm saying, well, maybe not. So is that okay that I've done this? Sure. Well, let's think about it for a moment. So, for different drawings, x2 minus x1 could be positive or negative. Now, if x2 minus x1 is positive, then the absolute value doesn't do anything. So if x2 minus x1 is like 5, then absolute value of 5 is 5. and then we'd square it and get 25. But what if x2 minus x1 for a different drawing is negative 5? Then that one is saying that, okay, take the negative 5 and calculate absolute value to get 5, and then square it to get 25. But this one is saying, forget the absolute value. Just take that negative 5 and square it. What do you get? You get 25. So do you observe that because we're squaring, we can just forget the absolute value? It's not necessary. All right. So then that's good. Now I want to solve for D. So solving for D. So I wrote the same thing, except I didn't write the square, because what I want is I want to get this D by itself. So in some sense, the squaring has to switch sides and go to the other side. And when the square switches sides to go to the other side, what does it become? Square root. But remember, we've said it so many times, there's an inequality that goes with it, and that is that we need it to be the case that D is greater than or equal to 0. So that's the algebraic manifestation of the fact that if you live in a two-dimensional world and you're looking at a line segment, you can't say that this is a negative line segment and that one's a positive line segment, because from this side it looks one way, and then you walk around to the other side and it looks the other way. Okay. So now, finally, we can make a nice modification here, or just another way to look at it. We can say D is the square root of, and right here I'll write delta x squared, and then plus delta y squared, interpreting the drawing like this, that delta x is going to be that, x2 minus x1, and delta y is going to be that one, y2 minus y1. Okay, so what that means in the picture is that this is delta y, and this one is delta x. So what we're saying is that you calculate that and square it, you calculate that and square it, you add it up, and then compute square root. All right, let's do it for one example. So, for example, find the distance from negative 3, 4 to 5, 1, like that. All right. So then, as a picture, it would look like this. So plotting both of those points, so the fact that that one says negative 3 means it's on the left side, and the fact that that says positive 4, that means it's on the top side. So that point is in the top left. So negative 3, so left 3, up 4. So something like this. And this one, using top, bottom, left, right, where's this one? top right. So it would be like this, ish. So in the end, what we're asking for is, what is this length? Okay, so let's calculate it very quick, because we just have 30 seconds left. Very good. So delta x, well, that's that x minus that x. So that'd be 5 minus 3, like that, I guess. But that can't be right. And then we have 1 minus 4. So what's wrong about what I've written here? So I did that x minus that x. Right. So it's, if you put parentheses around it, around all these things, and say that it has to look like that. So 5 goes in there, and what goes in that one? Negative 3. So this would be 8, and this would be negative 3. And therefore the distance is the square root of 8 squared plus negative 3 squared, which is 64 plus 9, which is 73. All right, so that's all that we have for today. I hope you have a wonderful Friday.